Thanks for coming, everybody. I'm Jim Boulton, and I'm a kind of enthusiast of the history of technology. And I've written a comic with Lynn on how she invented VLSI. It's been an 8-month process. It's been a lot of fun, mostly. Hey, Lynn. We've had a few ups and downs, but mainly ups. Lynn's quite a hard taskmaster. And but I think we've come to a pretty cool. We're happy with that comic. We've got a pretty cool comic, we think. So we're going to be talking this evening about two things, really. First of all, we've been talking about Lynn's invention of VLSI, the technology that enabled today's billion transistor chips. And as Lynn already knows, we've got some people in the room who worked in the VLSI team at Acorn in the 80s. You've met at least one of them. And yeah, so we're going to be talking about Lynn's invention of VLSI, and then we're going to be talking about the process we went through to create the comic. And then there's going to be some questions at the end. But the first thing I'm going to do is talk about a little bit of the background about how this project got started. The comic is called Lines in the Sand. And obviously Lines in the Sand has got a few references. We're talking about the pathways on the silicon itself. Of course, silicon is largely sand. We're talking about some of the kind of arbitrary lines in the sand that exist in society and how they impacted the design methodology at the time, and how they impacted the AI we used to actually create the comic. Also kind of represent some of the illustrators that I talked about, working with them and working with AI, how they kind of had some lines in the sand that I absolutely didn't want to get involved in AI. So it's got a few different references. Everyone knows Lynn. I'm Jim. And my relationship with the Computer History Museum started through an exhibition of websites that I've got that I display on computers from their websites from the 90s and computers from the 90s on browsers from the 90s. And I've been partnering with the Centre for Computing History for the past few years on that. We did a great exhibition a couple of years ago in the Grand Arcade, which was supported by Raspberry Pi. And yeah, got a lot of interest. There's the exhibition. You can see that in the top left. I also try and interview some of the people who made the websites. The guy in the top right is Alan Tage, and he invented the first internet search engine, Archie. And I was trying to find out about Alan, and I was Googling him, and nothing much came up. Oh, this is unusual. The person who invented the search engine, I can't actually find much about him by searching. And then I discovered he went to school with my neighbour. He's from Barbados. My neighbour happens to be from Barbados. I worked out they kind of were at school together. And I got in touch with Alan. He was coming over to the UK. We spent the day together, and I interviewed him. And then I ended up creating a comic about his invention of the search engine. Written a book on the history of the web. And as I mentioned to a couple of people, for my 50th birthday, I was born in 1969. The internet was invented in 69. I went to see Leonard Kleinrock, and I went to the room where the first message was sent over the internet and spent the day with Leonard. And I wrote a small comic about my conversation with Leonard, and went into schools and talked a little bit about the origins of the internet. That went down well. So I did a comic about Alan. And I thought it'd be cool if you could do a series of comics on unsung heroes. We hear a lot about the entrepreneurs who kind of exploit technology commercially, but we don't hear a lot about the people who actually created the infrastructure in the first place. I thought it'd be good to tell their story. And I've got this kind of big idea that I'd like to do a graphic history of the information age, going all the way back to the Manhattan Project and Vannevar Bush and his first ideas about computer networks and the internet. But I realized there was a big gap in my knowledge when it came to the microchip. And if I was going to write this graphic history, then I really should find out more about the history of the microchip. I knew about William Shockley and the invention of the transistor and Shockley semiconductors and Fairchild and Intel, but I realized that's where my knowledge stopped. When I started looking into it, one person, all roads led to one person, and that was Lynn Conway. And what was amazed at was actually that Lynn had been based at Xerox PARC. And we hear a lot about Xerox PARC, but it's all about the GUI and it's all about small talk and object-orientated program. But we don't hear a lot about the VLSI. And I thought that was quite a surprise. So I thought to myself, I found my next unsung hero. So I emailed Lynn and asked if she'd be interested in creating a comic about her invention of VLSI. And happily, being the enthusiastic person that she is, Lynn was happy to get involved. So, and over the last 8 months, yeah, we've come up with a comic which you've got in front of you now, and hopefully you've had time to read through. And I think now Lynn's going to take you through some of her experiences of creating VLSI. Then I'm going to talk a little bit about the creation of the comic, and then we're going to open it up to questions. The other 2 comics I worked with illustrator friends of mine, Once Bitten, Twice Shy, or 3 times shy. I couldn't actually persuade an illustrator to get involved with this comic, so I actually ended up creating the images in the comic using Midjourney, an AI image generation platform, and it's very interesting looking at some of the biases that came through. And as we were creating the comic, we realized that some of those biases kind of reflected the biases, the societal biases that Lynn had to put up with in the 70s and 80s. So we're going to be talking a little bit about those later as well. But now we're going to hand over to Lynn. So Lynn, I'm going to stop sharing my slides. Okay. And you can say a little bit about your background and how you invented the world-changing technology, VLSI.
Well, hi there, folks. It's going to be fun sharing these stories with you and this little project that Jim and I have had going on. Because, you know, in our own way, we're exploring, just having fun out there, trying things out, trying to figure out what's happening, what we can use to do things. So I actually view this little adventure we're having here very much in the spirit of just exploration in general. It's a kind of fun sort of thing to do. It feels a little bit like back at PARC. You have a world unfolding. There's a lot of things happening around you. What can you put together from that world to make a new world? What affordances are there at that moment that you might be able to combine in some weird way to do something new? And, you know, of course, now everybody's talking about AI. Well, what is AI? Everybody has a definition, but are we sure what we mean? Do we need to know anything about chips to know what it is? Maybe math, maybe actually chips. So just kind of getting in the spirit of the moment of having fun doing things, which I've always enjoyed doing. I get involved in a lot of projects like this. Just something catches your imagination. And part of what wrote me into this was the fact that Jim and I talked about it, but then he lost his illustrator. And it's like, oh, okay, you don't have anybody to actually draw the art for the comic. So that kind of squashed it for a while. Then there's a delay, and then here's the idea. Hey, I'm going to try to use AI to make the illustrations. Why don't we see how that works? And I thought, oh boy, AI, right? Like, who knows what this is going to be? What AI? What? And of course, it turns out that comic people have cooked up AI they use to make drawings. Maybe the comic people who don't do good comics, but would have an idea for a comic. So I thought it'd be fun just to get involved in this project. And let me tell you, it has been, because fighting with the AI to create the images has actually ended up being quite an adventure. You know, here we're using new tools in a new world of stuff, crazy stuff being generated. So, well, let's do this. Well, it actually turned out the AI was pretty funny in what it would generate for images. And Jim's going to talk a lot about that. But let me just go to the story of the VLSI. You know, here remember, I'm an old timer. I'm 85 years old, and all this happened, you know, like 45 years ago. Actually, 40 to 50 years ago. And one of the ideas that appealed to me in a comic is there's a few key things that people don't know about what chips are, or what foundries are, what TSMC is, what ASML is. There's things people don't know. They have no way to kind of know the gist of it. It's kind of like we're always in a world where we wish it's the things your parents never told you because they're just learning them now. So when they were young, you know, they never could tell you those things. It's sort of really what underneath it all is actually happening. So we took off on an article that appeared in the New York Times on August 4th. See, a lot of the actual things that happened on this comic happened in July and August. It's fairly recent, and then you know, put together and printed up for this gathering here. So if you were to take a look at the opening page of the comic, what you would see is some familiar things that people talk about. First frame, silicon chips, pioneer of the information age. Well, what's a silicon chip? What's the information age? But you know, you can say those words and just like everybody understands it. I'm not sure people do understand it. The most powerful silicon chips are designed in the US. Well, people could argue about that, but many of them are. You know, we think of the current world, think of the stuff Apple's creating. But they're printed in Taiwan. So there's an image showing a line going from California to Taiwan. Well, what do you mean they're printed in Taiwan? Well, Taiwan's where TSMC is. Well, what's TSMC? It's an international foundry that was founded by Morris Chang in 1987. So this is in this New York Times article. And in it, he mentions this book was the first part of the puzzle. And of course, the book he's referring to, and I think some of you in the audience have it, is this book. Okay? And that's a book that I and a colleague, but mostly I wrote back in the period of 1977 and 1978. And forgetting from what all the stuff that's in the book, there's an overriding thing that the book doesn't really say, but it's like one of those things your parents never told you, or one of the things your mom never told you. And what it is the foundry model that the book evokes separates microchip design from microchip fabrication. Operations that were previously carried out within the same company, vertically integrated. And you might wonder, why was that happening? And did anybody think about it? It's just the way it evolved, and we can go into that. But the main thing to imagine is that when people think of, okay, the problem with Taiwan, what if Taiwan gets invaded? All of a sudden, who's going to make chips? Because so many of the world's powerful chips are made by TSMC in huge factories, so to speak, on Taiwan. Well, when you say they make them, what do they really do? Well, the thing is, they actually print them. They print patterns in the silicon, kind of like if any of you are familiar with screen printing. You can build up layers of material so that in a screen print, you get beautiful colors of all sorts. By using stencils when you put each layer down to decide where that color goes. Now, it turns out what TSMC does is it prints the designs created elsewhere. And I think, you know, people, when you think of ARM and you think of all the chips that ARM has created, they don't have necessarily, none of the companies that create the knowledge that gets put into form for printing, they really don't need to have a printing plant right next door, because these kind of printing plants are very expensive and it turns out very capital intensive. So now in the United States, when we talk about we want to make chips, well, of course, what the people in government do is say, well, how do you make chips? Well, build a printing plant, you see? I want you to think about that for a while. The printing plant isn't where the ideas for printing come from. See, they come from other people elsewhere. And it's this separation that's the thing that's the embedded message of the book. So anyway, this comic goes through that. And it tells you a little bit about where the ideas on how to do that came from. And the prior history of it all is very interesting, because in the old days, before the microprocessors were being created, back in the days of integrated circuits and then medium scale and large scale integration, what was happening was the integrated circuit manufacturing companies took very simple designs, initially just things like, for digital systems, things like logic gates, and figured out how to create the patterns that would print those, you know, a few logic gates on a piece of silicon. And how did they do it? What they did was they cut the patterns for the artwork in big sheets of what's called rubylith. It's like a plastic material. And what you can do is you can cut the patterns in that, and then you can overlay them to make sure that each layer is in the right place, aligned with each other. And in the process, create the artwork, which you then photograph and shrink and shrink and shrink down for making the little stencils that are used in the fabrication plant to print that artwork into the silicon. So when you think of that, the semiconductor industry, as it expanded to when you get to companies like Intel, and they first made their 404, the artwork for their microprocessors was cut out of rubylith. Okay? It was manually made. So I want you to think about, you know, those were fairly big processors. They had a few thousand transistors. All of that was like skilled artisans cutting this and checking for design rules and making sure everything overlaid its thing right. Imagine doing screen printing like that and trying to get finer and finer details. How would you ever make the stencils? Well, it turned out you need to end up using, you need to make them out of computers. And the little story is in there in the comic. But more importantly, you need to think about complexity, because the thing you were making, once it got beyond a certain scale, was it become so geometrically complex that you really couldn't capture the design well. And so a lot of this goes to some design rules I came up with enable the process to print designs to finer and finer scales, because they were rectilinear. There were no curved geometries in them. It also talked about the design rules as being scalable, so that if you had a design, let's say you have something you'd like to print it many, many times, you'd like to use it in all kinds of things, but you'd also like to be able to shrink it down so it can be put into a thing where everything has been shrunk down, part of a bigger mosaic. Well, rules that enable that enable a number of things and enable computers to more easily manipulate the design rules. And if you encoded the designs in computational form, in digital form, then those designs could be scaled, reused. Open sourcing became something one could think about. And a number of people working at a given level of design could share designs with each other, maybe team up on a combined design, and then glue their designs together in digital form, and then make the mass out of that you could print on silicon. But let's just step back, and I just want to show you a couple of things. We're talking about chips, and I'm thinking that one way I like to talk about this stuff is just to show the actual artifacts. Here's some historical artifacts. This, and I get it in where you can look at it. That's a silicon chip. It's a thin little rectangular slab of silicon. Okay, but I think as I get it closer, you can actually see that there's something on that silicon surface. Let's get it to focus a little bit. If I tilt it, you can see there's some patterns. There we go. You can see them etched on that surface. Okay, well, what is that? What is that stuff? Well, let me show you with a visualizer what a silicon chip is. So I'm going to switch to shared screen, because what I'm going to do is show you there's a slab of silicon before anything has been printed on it. Now, imagine you're screen printing, you've got a stencil, and what you want to do is you want to put down, we'll call it the diffusion level. And what this is we're actually using screen printing, in a sense, a level of pattern. And it's done kind of photographically. We put photoresist, we expose it through the stencil, we develop it, and then we implant ions. We create essentially little wire lines in the surface, on the surface of the silicon. So just imagine a bunch of paths there. And we use a computer using design rules to create the patterns in a digital form so we can easily make the mask to do it. Then what we do is we put a layer of silicon dioxide. It's an insulator. It's kind of like we're making like a little printed circuit board. And if you look at that now, you wonder, okay, all we have is wires and some insulator. That is kind of like a printed circuit board, isn't it? Well, then what we do is we put another layer, and we'll call this polysilicon, but this is just the red layer. Green layer was first, and oxide, then we have this red layer. Still doesn't look like much is there. All right. Then what we do is we put another layer of oxide. And by the way, this is the NMOS back in the day when this work was first done. We use CMOS now. There's a variant. There's a few more layers, but everything works pretty much the same conceptually. And then what we do sorry about that. Let me line this all up so it keeps looking the same. And this is going to stop pretty soon. And I think we'll be amazed by the result. Okay, placement of contact cuts. Remember those layers of oxide? What we do is, this is a layer where contact cuts can be made and are made, where we drill down through those layers so we could connect particular ones together, depending where we drill the hole, okay, in another part of the process. Then finally, we have a layer we call metal. And what is metal? It's aluminum. Now, all this is done in a vacuum chamber. So the actual handling of all this is tricky because all these things have to be processed in vacuum. So the physics, the chemistry is complicated. But in the end, here's what we end up with. Now, turns out, amazingly, that's all there is. And you might ask, well, where are the transistors? Where are the transistors? Because all that we put down are those three different layers, like a printed circuit board, and connected things together like a printed circuit board, but there don't seem to be any electronic machines in there. It's all just wires, okay? This is where it gets interesting, because that is all there is, except there are transistors there. There really are. But where the transistors are is everywhere. Wait a minute, let me mirror this so I can see what I'm doing here. That's why I was getting confused. I had it mirrored, okay. Remember the green wires and the red wires, the first two we put on? Well, it turns out, conceptually, wherever a red wire crosses a green wire, you see that little cross point, that little rectangle where they cross? That's a transistor. In other words, the magic of the process is that wherever you put a green wire over a red wire, it creates, and I put a diagram here, what amounts to a voltage control switch. If there's a high voltage rather than a ground on this red wire, it pushes that switch closed, and the green wire will conduct electricity. If the voltage on the red wire is lowered, the switch opens. And I won't go into the details of that, but they're in the book, not the comic, the book I showed you. But there's something really amazing about this. And that is that if you give a computer engineer, or especially a computer architect, voltage control switches, lots of them, guess what they can do? They know how to hook them all up. It almost looks a little like building out a giant model railroad set, okay? What they know how to do, now I gotta find it. Ah, I found it. If they know all the computer science and all the mathematics, and I'm going to bring this up a little bit and turn this down a little bit. To build a microprocessor out of it. And what this is this is what is in the frontispiece of the book, showing the microprocessor that can be created using the knowledge that's in the book, starting with how red over green makes a switch. And that is the knowledge that comes from the vast, long human history of the mechanization of mathematics. And there's just, untold inventions down the millennia and the centuries. Look at the abacus. When you see an abacus and you start thinking of the technosocial knowledge and transmission of the knowledge of what it is and how to use it, that's knowledge that is accumulated on down through George Boole's Boolean algebra, that actually the laws of thought, how logic works and how simple it can be mechanized, which was done by Claude Shannon in a master's thesis at MIT. And so there's a vast knowledge, not in semiconductors, but in mathematics and in computing and in the mechanization of computing. So what's so interesting is we have this quandary where people in the world think that the foundry creates the chip. But what it is more like is a publishing house that prints the chip. But think about it. The people that print something don't even need to know the language. In fact, very few of the people printing the chips in a foundry have any clue how they work, what they are, what they, in a sense, say. So the computer architects who come up with the knowledge to know how to innovate these vast amounts of digital machinery are the ones who are in a sense, the novelists, the writers whose works are being printed. And when you stick electricity into them, they come alive and animate things. You see? So it's a kind of funny situation where there's so much more activity going on than just in the foundry. In fact, vastly more. And there's so very many more people involved in the design of these things than there are in the printing of them. Do you see? And so that's kind of the story that we were thinking about telling in this comic. And it's sort of like, how do you explain to young people, okay, what the elders never told you when they learned how to do it? You see how it kind of inverts itself? And also, we've been toying around with AI to figure out how to exploit AI in telling such a story. And I think I'll turn it back to Jim now, because the whole thing there is, wait till you hear how the troubles and the fun we had trying to use AI to do this comic.
Okay, so I'm very quickly gonna take you through the story itself. Lynn's already talked about the fact that we wanted to explain what the foundry model was, and that a lot of the chips made in Europe and the US, or designed in Europe and the US, but they're printed in Taiwan. We're wondering how to start the story, but as Lynn said, we had a lucky break in the Morris Chang was interviewed in the New York Times just as we were doing the comic, and mentioned Lynn's book, that it all started with this book. So we thought that's got to be the start of the comic. It's meant to be. And then, having previously worked at IBM, Lynn went to Xerox PARC, and where amazing things were happening. And she she headed up the team that was exploring microchip design, and she was collaborating with Carver Mead, who was a Caltech professor, and he'd actually coined Moore's law, the fact that the number of transistors on a chip were going to double every 18 months. And Lynn realized that meant, Rublev wasn't going to work anymore. There needed to be a revolution in how microchips were designed. And actually, Lynn, you talk about it being a self-fulfilling prophecy, Moore's law. Do you want to talk a little bit about that?
Well, actually, I sort of view it as it's an evolutionary process. Once you had a doubling every 2 years in everybody's minds, people across the vast landscape of people planning chips, everything from the people planning what they're going to market in the future to those behind the scenes trying to work the processes and the lithography and the designs. To meet that point, you end up with a vast human collective that synchronized itself to a certain expectation of what's coming every couple of years. And it turned out that the advances just kept going because amazingly, as you made the lines finer, the silicon just kept doing its thing and the transistors kept doing them. But guess what? Every time you made them smaller, they also went faster because there was a shorter distance across them for the electricity for the electrons to transit, or the holes to transit, depending. And so one can really view it as a synchronization phenomenon, kind of like fireflies, one at a time blinking a few, but then suddenly they all start syncing to each other. And so everybody involved in this process just took Moore's law as a law, and the plans kept working until it started to kind of run out recently as there are a few problems, blah, 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 blah. But this amazing thing actually almost seemed like it was almost taken as if it were a physical law, when in fact it's a law about how technosocial system dynamics works. But that's another topic.
Yeah, and I wish you'd come up with the fireflies metaphor when we were doing the comic. That would have been really useful. We'll do that. We'll use the fireflies in the next edition.
Right.
And then Lynn and Carver, they went across Silicon Valley, going to all these chip manufacturers and talking to them about how chips were designed, the challenges, what was happening around the corner, et cetera, et cetera. And Carver Mead used to go and meet with the management, and Lynn used to go and talk with the engineers. And because they just assumed that she was Carver Mead's assistant, they were very open and they kind of let all their secrets out. So Lynn ended up having this kind of encyclopedic knowledge of chip design, but more importantly, she realized what they didn't know, and she was able to kind of fill in the gaps. And as a result, she was able to come up with VLSI and the design rules that she's just been talking about. But when she kind of shared them with the wider group at Xerox PARC, they were kind of poo-pooed. They said, it can't be this simple. If it was this simple, Intel would already be doing it. This can't be the solution. It was kind of a bit dismissed. And also, I think there was possibly some sexism involved. And Lynn didn't have a PhD, so she was, potentially a bit of snobbery involved. But Lynn knew she was...
Comment on that. I wonder who my advisor would have been back in the day. That I'm just kind of joking on my history, but that's another topic.
Yeah, and Lynn knew she was onto something, and she was wondering how to prove it. And Lynn is a very well-read woman, and she knows her history. And her hero was Charles Steinmetz. Do you want to tell us a bit about Charles Steinmetz?
Yeah, I think the amazing thing about Steinmetz, but he had a lot of obstacles in his life. He was born with a spinal disorder and it was physically terribly handicapped. But the thing about him was that he didn't let that stand in his way. He was just very intelligent, very actually playful, creative, and he came up with a way of simplifying alternating current so that the average engineer could use it. And he published his ideas in scientific journals of the day in the 1890s and became famous among electrical engineers for these ideas. But it turned out, professors writing things for the journals may make them famous among other professors and scientists, but it doesn't actually get their work doing anything. So what Steinmetz did is after 1910, it's making a lot of years with none of this stuff taking off, he sat down and he wrote a couple of textbooks on the mathematics and the applications of his basic ideas. A lot of it was just simply based on a simple notion that constant frequency AC is steady state. And something at steady state, you can do algebra on it and do all kinds of computations, just like it did for DC. But you had to use complex numbers. So he introduced what he called the natural number. They didn't even use the term complex number in the day. He introduced that in the core of some books he wrote, and he spun out how it would all work and mapped it all out. And so I always saw those books as being kind of the model of what to do when the day came to do VLSI. And I even had a picture of him on my wall at MIT when I was doing that stuff. So it turned out that as soon as he started teaching out of those books at Union College, which in New York, which was, he was working at GE, but he started teaching those things, engineers picked up on it and just started doing it. It almost maps one for one into the VLSI saga, you see. And I don't think people in Steinmetz was very famous before he died. He was viewed as the first one that created the electrification of America. Okay, but few people really caught on that it was that core idea. There's an analogy to the design rules in VLSI that gave this central point that made everything click and connect together. You know, you got some giant power things and you put it together, and boom, this whole thing, you know, lit up and took off. And so his was on a big scale, this stuff I was doing just on a fine scale. So anyway, that's Steinmetz. Amazing.
So inspired by Steinmetz, Lynn decided to write a book. And because she was at Xerox PARC, it was probably the only place in the world at the time you could self-publish. She actually had the Alto, they had the Bravo word processor. They could actually create a book themselves. So Lynn went ahead and did it and kind of ignored the fact that the work was being dismissed by the powers that be. Now, one person who was very supportive was Bert Sutherland, Ivan Sutherland's brother. He could see how significant the breakthrough was. And he was an advisor at MIT, and he said, Lynn, you've got to go and teach this stuff. So Lynn's plan's coming together. She's got a book. She's now potentially got access to some students where she can actually start distributing this knowledge at ground level. Lynn had actually been at MIT in the past, so she knew how it worked, and she knew how to get most out of the students there. And she realized that it wasn't really the theory that got people excited. It was practical stuff. It was building stuff. It was actually, you know, having an artifact, a product at the end. So she decided that she was actually going to get students to design the chips in the first half of the course and then get them produced in the second half, which was hugely ambitious. Chip in when you want to, Lynn.
Yeah, what it was is by then I was able to teach, actually more or less guide would be a better word for it, guide students who were already very well educated. These are people that were seniors or usually master's level students in electrical engineering and computer science who knew all about the electronics, they just didn't know how to design chips. And to create a course that compacted everything into a half a semester, about 7 weeks, was with all you needed to know, but nothing you didn't need to know in order to start designing the chips. And I think the main thing is to know what to leave out. You see, how do you produce the compact version of here's all you really need to know to start, assuming you already know all about electronics. And then in the second half, they did their designs. And then after the course, I had arranged to get those fabricated at a lab at Hewlett Packard, nearby where we were at PARC, and get them back to students early the next year. And so the thing about it is these weren't projects that I defined for them. The idea was they were to invent their own thing they wanted to design something, okay? And guess what? Some of the students are pretty bright people. Jim Cherry did a foundational project in computer graphics where he built a chip to mirror and rotate image data. Think about that. And Guy Steele, another student in the class, a PhD candidate at the time, designed a Lisp microprocessor as his first design. So imagine, think about that. So these students were innovating at the architectural level in a new medium, in silicon. And so that's where the breakout was. It wasn't just training people on how to do a basic task. It was taking really bright people and presenting them with a new medium in which to do their art that gave them vastly more power than they could find any other way. So I think this course and the mystique around it kind of broke out and started infecting the research universities because they would want to have courses. How did MIT do this? And of course, it turned out my name was not really associated with it. People thought MIT did this. Isn't that cool? That's known as flying under a false flag. You can go far that way sometimes. You can accomplish almost anything if nobody knows what you're doing. You see? Because you do it and it just arises out of this system, namely MIT, and they are the place it came out of. So there's a bunch of weird messages in all this. And I hope you find it sort of intriguing or fun or wild or something, because it felt like it at the time.
So that first course at MIT was a huge success, and kind of word spread across the ARPANET. And you've got a analogy where you compare the ARPANET and the microchip with the railroads and the telegraph, and say one couldn't really exist without the other.
Yeah. Yeah, I think if you look at the ARPANET at the time, sort of the precursor to the internet and everything else we know since. One thing it did, it connected the really major EECS departments at the research universities, because that was where the contracts to kind of exploratorily build out the ARPANET were sent by ARPA, now called DARPA, Defense Advanced Research Projects Agency. And so what was amazing is at PARC was on the ARPANET. So I actually not only had access to all the great tools at PARC that were being made to do computer graphics work, what you see is what you get, how to create and print artifacts on laser printers, all of which was new. So the things we were printing as this precursor book looked like almost like a real book, and even had the color diagrams in them because I could print them on a laser color printer at PARC. So what's really interesting is to think about how it's the artifacts moving around and how do they move around, and then the communication method, the transportation method to move them around. So in a way, I've patterned a lot of this on the co-evolution of the railroads and telegraphy during and after the Civil War in the United States, where what one would find is wherever the railroads went, you had to have telegraphy, because you needed that so that you could kind of mostly avoid trains running into each other. You'd know where the trains were. Okay? But it also meant where the end of all the way to the end of the train line, where it was, you could send messages, say, well, what's out there? Did you find anything interesting? No, this is a bust. We never found anything. We were running this spur up there. We thought there was going to be gold there or silver or something. Never was. So you can see there's a lot of these are technosocial processes where it's humans doing stuff with stuff, exploring and moving around, sending messages to each other. And so we almost see history reinventing at a higher rate past adventures people are going on. Earlier analogy would be when people first realized they could go over the horizon on the ocean and manage to get back someday, because they now had instrumentation that let them do that. Compass, maps, astrolabes, and so forth. And then you have the age of exploration unfold. Kind of always this similar process. So the process that ran here is sort of how did these chips, and then the internet, ARPANET, that built up using them, because a lot of the early chips that were fueling progress were chips that were used in building out the ARPANET. Can you imagine? You sort of see how this is happening? And anyway, I'm talking too long here. Let's continue with the story.
I think the interesting thing here, well, there's loads of interesting things, but the fact this was a really small team. But the fact that a book had been published, the fact that it had been run at MIT, the fact that Hewlett-Packard were printing them, the fact that Lynn put Mead's name on the book first, meant there was all this material that gave VLSI credibility. And as a result of all of that and the success of the course, loads of universities across the ARPANET kind of clamored to run the course the following year. And at this point, it was a real challenge. How are you going to scale it up? How are you going to scale it up? It's all well and good doing for one university, but how are you going to do it for for multiple universities? But Lynn, being Lynn, didn't let that worry her, and she persuaded a few of her colleagues, Alan Bell and Martin Newell in particular, to create a design system that would allow students to do just that. So the course ran the following year with, I think it was 9 universities and 124 students and researchers. And one of those researchers was Jim Clark, and he created a geometry engine using VLSI. That was his student project, which he used to actually launch Silicon Graphics. And the money made from Silicon Graphics kind of invested in Netscape and half of Silicon Valley. So the dot-com boom had its kind of roots in the student project that Jim Clark made when he was studying VLSI. I'll carry on. Such was the success that the book was published, the book we have in front of us, which gave it kind of massive profile and expanded beyond those 9 universities and started to catch the eyes of the wider industry. And one of those people was Morris Chang at Texas Instruments, who was getting a little bit disillusioned with their focus on what he thought were calculators and toys and not very ambitious projects. And so when he was approached by the Taiwanese government to set up a semiconductor company, he jumped at the chance, and we're back to the beginning. And as a result of that kind of foundry model, Taiwan now is like a hugely important place in the world with hugely important geopolitical value and implications. And the foundry model has allowed small kind of agile startups like Apple and Nvidia, for example, to design their own chips and products without investing massively in the infrastructure that makes that possible. And it's all thanks to Lynn.
Well, and the team. I mean, there's an amazing cast of characters that were involved in the team at PARC, and stories to be told another day. But the thing was really weird about this project, Jim, of course, was fighting with the AI and how actually fighting to make something happen. We actually had a lot of conflicts, mainly because the AI was doing so many weird things. And we would have conflicts, but then it seems that's when the creative juices would flow, when we actually get to how to break a log jam conceptually. So the thing behind a lot of this is I'm finding all of this fascinating from the standpoint of, thinking about what is an innovation, how do innovations happen, how do they spread, how do they propagate and diffuse, how are they selected? Some stick around and some don't. And when we look at all the artifacts around us, do we ever think of the history of those and how far back it goes in many cases? Depending on our cultures, the tools we use to eat food, the actual practical tools, whatever we use to brush our teeth, whether we use candles or lamps or this or that, all of the artifacts around us have this huge, long history, which also informs us about what we might do next as we mix and match and combine them in new ways. And the AI, in some bizarre way, almost is capturing more and more of that history and just tossing it in front of us, all scrambled up in new ways, which we found out. You might mention some of the particular frames where the AI just did weird stuff. And it is still in some of them, like on that first page.
Yeah, so I'm just going to go and mention a few of these, and just so we used Midjourney to create the images. When we looked into Midjourney, I had a look into the training set, and it's based on 5 billion images that have been scraped from the web, and I actually realised that it's actually a lot of these. There's loads of these. There's Stable Diffusion, there's DALL-E, there's a load of these AI image generation tools, but they all use the same training set, which is, perhaps a bit of concern, and it's all been scraped from the web. So it's a certain data set that we're looking at, over the past 30 years. And actually most of it is from like Pinterest and Flickr and DeviantArt and Getty Images. You can see there's these big pools of data that a lot of these images are grabbed from. And the reason they come from those sources is because they needed images that were tagged with the text description of what was actually in the image. They ended up with a data set of 5 billion cleanish images that were kind of had the right metadata associated to them. But when you have a look at it, obviously a lot of those images, first of all, it's young people. It's majority of people are kind of under 45 who've kind of uploaded those images. So that's kind of one bias in the system. I was expecting it actually to be more men, but actually, like Pinterest is 72 or 73% female. So there's not necessarily that bias there, but most of the audience are based in the US. So it's definitely a kind of like a narrow-ish section of society that have provided these images, which has implications. So this is, I uploaded those 2 images to Midjourney with you can't quite read it. It says a comic book illustration of a man and a woman looking at a comic book and smiling. I uploaded those 2 images. Right, and that's the image that we got. And obviously, Lynn and I are attractive people, but I'm not sure we're that attractive. So everything was kind of like made more attractive than it is in real life. And I don't know if that's to do with the fact that it's a comic book illustration, and a lot of comics, would use attractive imagery, or whether it's the fact that there's a lot of models and filters used on the internet. But the first thing was everybody was kind of made more attractive. And then there was a couple of, we didn't actually use any of these, but these, I just tried to upload some diagrams and with the comic book illustration as the prompt, and I'd get these kind of images. So you wonder what on earth's going on there. And it wasn't a coincidence. So I kind of like, uploaded these ones, and you get women in bikinis. So I'm not quite sure what's going on, but obviously there's some bias going on in comics and probably in that data set. So that's the original image. I uploaded that image of Lynn from Wikipedia, and I said, imagine this woman aged 35 in California in 1973, and that's the image that it created. So I used that as the base image when I was trying to generate the rest of the images, and there's some consistency. Those 2 are fairly consistent. But I think these 3 images, particularly bottom one on the right, bottom right looks similar, but the other 2 ish, but it's quite difficult to get that consistency. Now the most worrying thing though was this. This is the first panel in the book, and actually I wasn't trying to create a map of the world. I took this was from a prompt later. The prompt I asked for was it's a map of America. And then it's I think it's like information, words spread across the ARPANET. So it's the caption from the panel, a comic book illustration, and that's the image it created. So in its defense, I didn't ask for a map of the world, I asked for a map of America, but you can probably see there's one big omission, like it's just missed Africa entirely, which is a bit of a worry. You would think that there was plenty of data there on maps. And when I said kind of add Africa, it added an African woman. So, obviously, with that's a concern. That something as simple as that can be overlooked. As I said before, we've got a lucky break. So that's Morris Chan, as according to Midjourney. That's what Morris Chan actually looks like. But this was the article in the New York Times that popped up when we're in the middle of working on a comic. And the other thing that this isn't really to do with AI, but it's kind of maybe influential. When we were looking at Xerox PARC and thinking about all the breakthroughs, and you go to the Wikipedia page, it talks about the Alto and the GUI. It doesn't mention VLSI once. And all the distinguished researchers, you know, happen to be men. So if the AI is kind of using that as a data set, obviously looks like there's bias involved. And this image is kind of like was a bit concerning. So this is the image of Carver Mead and Lynn visiting Silicon Valley. And when I first put the prompt in, it had them holding hands, right? Every single one. I never asked for it to be any kind of romantic thing to it. It's a man and a woman with a back view walking towards the building in Silicon Valley, and it's holding hands. When I asked them not to hold hands, it got even worse. So inappropriate touching. And in the end, the final image, when I said standing apart and not holding hands, as you can see, they're still standing quite close to them. The image on the right is the one I ended up using, but I had to move them apart and yeah, make Lynn a bit taller. So yeah, and things going on. The other thing, yeah, so this is Charles Steinmetz, and when I put in the prompt that he was, you know, had a hunchback, it kind of came up with these almost kind of comical type images. And, you know, Lynn's saying, actually, these are totally inaccurate and inappropriate. It's a heroic figure. And, you know, we need to adjust for that. So, yeah, so we you know, eventually managed to force it to give us a classier image. And again, this is not so much about the AI, but it's about kind of Lynn and Lynn's attitude to things. So I was getting a little bit carried away, and I was talking about the fact that perhaps this is one of the first self-published books, and we shouldn't underestimate the influence this has had on kind of self-publishing. And Lynn was, no, you know, let's not go over the top about that, because it's important. Everything is kind of factual, and you know, this can potentially be used as a training data or at least a reference point for kind of future work. And I don't want to claim anything that can even be remotely challenged. So she didn't let me go on about her influence in self-publishing. Also, just to say, this is Bert Sutherland on the left. It wasn't just women that it made more attractive, like it made Bert quite dishy as well. And this was kind of an inadvertent kind of lucky thing that came up. I didn't want to put a picture of Lynn on the wafer particularly. That's the image that I uploaded on the left, and I just asked for a comic book illustration of it. And for some reason, it just hallucinated a picture of someone who looked vaguely like the image of Lynn. But we decided to leave it in because Lynn's reputation was kind of embodied in that chip. If that chip had failed, if that project had failed, Lynn's career might have been over. You know, she was already kind of being a little bit being dismissed, and people were saying this was never going to work, and you know what she's thinking of, she's getting ahead of herself. So actually, in some strange way, the AI had actually managed to imagine and combine that, you know, Lynn's reputation was kind of pinned to the success of that chip. So in that instance, the AI was almost like a collaborator, a creative partner. So silicon graphics, this was another example of Lynn being really hard on me. And this is one we, you know, I don't think we had a lot of conflicts, Lynn. We had a few, but I wouldn't say it was a lot. But this was one of them. And the reason was because Jim Clark's project was a project that he did while he was studying under Lynn on the VLSI course. And I wanted to put in Andy Bechtolsheim, who founded Sun, because he was also a student of Lynn's, you know, and he had done the VLSI course. And inspired by the Alto, I actually found a quote in the New York Times where he said, I realized that if people were going to be designing chips using VLSI, they would need something like the Alto. So that's why he kind of set up Sun Microsystems. Right. So I tried to put Sun in there as well. And Lynn was like, no, you know, Andy's project had nothing to do with him setting up Sun, whereas Jim's project absolutely did. So Jim's in and Andy's out. So Lynn was kind of really like super focused on everything being 100% accurate, and all being direct links and no indirect links. So I felt the Sun was quite a good link, but it hit the editing room floor. And Silicon Silicon graphics building now is the Googleplex, just incidentally. So we kind of use the Googleplex building to train the model for the Silicon graphics. Lynn, for various reasons, felt like when she kind of left IBM and started Xerox PARC, she was looking over her shoulder. So this image is kind of Lynn looking over her shoulder. But actually, the more I look at it and the more I've been involved in the comic, I kind of start thinking of a quote that Lynn's become famous for, and that's, if you want to change the future, start living if you're already there. And I think Lynn feels to me like she is from the future, and she saw where the world was going ahead of everybody else. And that image that we saw previously, it's almost like Lynn is looking back at us. She's in the future and she's kind of looking back at everybody else. So I just want to say thank you to Lynn, and thanks to everybody else for coming tonight. And now we can open the floor to some questions.
Hello, Lynn. My name's John Biggs, and I used to work at Acorn, and was one of the guys, along with Jamie here, who got thrown out of Acorn to start ARM. Right. And in the early days of doing VLSI design, we just considered polysilicon to be red, largely because of your book. And there's a colleague who joined us, swore blind that polysilicon was green. And so Jamie would just like to have a recording of you saying that a transistor is made by red over green, so the polysilicon is red, so you can send it to our colleague and put to bed a 40-year-old argument. And actually, personally, I'd quite like to know, where was the inspiration for the colors? Did you inherit polysilicon being red, or did you come up with that yourself?
That I don't know. I suspect that I'm just not sure.
Okay.
I don't believe I came up with it, but I can't quite trace the where it came from. But the main thing to think about that is it's arbitrary.
Yes, of course.
And so,
which is why the argument has raged on for 40 years.
Exactly. So the thing is, the way I would answer it is, in the Lynn Conway book, red over green makes a transistor. And it does so because actually during the process, the oxide is made very, very thin where that crossing occurs. And so the polysilicon is very, very close to the silicon substrate itself, which means that when you put a high voltage on that, when it's very positive, electrons will be essentially drawn into that gap, because in the process, actually, there's a gap down on that green layer. You see, the weird way that all the layers are used is such that the red layer's mass prevents the green layer from existing underneath the red wire. So there's actually a gap. And that's what makes it a field effect transistor. So it's a little added information. But the answer to the question is just, oh yeah, in the book, red over green.
Right. Thank you very much.
You can choose whatever colors you want. And then we get to CMOS, you get more complication and blah, blah, blah.
It's a wrap.
Cool.
Well, you'll be pleased to know I'm working for a small startup here in Cambridge, and called Pragmatic, who they put thin film transistors down on a flexible substrate, and polysilicon is, well, the equivalent of polysilicon is still red. The metal that forms the transistor, we still draw as red.
Okay.
I think that might be a wrap then, Lynn.
Yeah. By the way, I was going to mention that there is a, if you go to my website is lynnconway.com. And if you go there, you'll see a picture of this issue of IEEE Solid State Circuit magazine. And that was the article in there where I reminisced about the revolution was really the time when I first really came out and kind of exposed kind of what had really happened. And of course, that was because I'd been living in stealth for decades. And so that was an obvious reason why nobody knew who I was, because I was living completely stealth mode and really had difficulty thinking about even facing having a lot of publicity surrounding my name and my work. But that magazine actually kind of helped reveal a little bit of the structure of this. And I think it's the structure of events. It's not so much the people involved. It's the structure of the events and the technosocial nature of that. That's really fascinating, and I find interesting to think about. So, one of my passions is really anthropology and archaeology. And I've been following work in that area for a long time, and informed me highly on how to do and conduct some of my work. So I guess if there's anything I recommend to folks is read any book that looks interesting to you, and you never know what you might come across that'll set you up to go out and do something wild, And anyway, it's just been a pleasure seeing you all, and wish you all well.